This is problem 23 of the QHack 2023 Quantum Coding Challenges, and this one is entitled One Bit Wonder. Now, similar to problem 21 on polywords, this problem is quite challenging because it requires to be familiar with a lot of different concepts. As a matter of fact, I would say this is the hardest problem of all the ones in QHack 2023, particularly because we have to use this idea of what they call qubits. And it's a very unconventional way to represent states. And also, I've been looking for some references on this and haven't been able to find anything. So there are going to be some parts of this problem that in the description, they're just given to us and we won't be able to completely clarify, but we will be able to get to a final solution. So what I want to do is similar to what we did for problem 21, is go over the main concepts that we need to be familiar with, and then we'll go into penny lane and code the solution. All right, so the first idea we need to be very familiar with is that of reduced density matrices. And again, I've mentioned this before, I have a full series on mixed states and density matrices, so we won't cover that in detail here, but we just need to remember that if we have, for example, a unitary U, and as an input we have state row 0 and row 1, where they're given by density matrices, well, the input state is just the tensor product of the two of them, right? And then after applying the unitary, well, the output state in terms of a density matrix is U dagger times the input state times U. So now if we want to find the density matrix associated with each of the qubits at the output, well, the way we would do that is, for example, for the top one, we're going to call that zeta 0. What we do is we take the total output state, which we said was U dagger times row 0 tensor row 1 times U, and then take the partial trace over qubit 1 of that complete output state. And similarly, for zeta 1, we do the exact same thing, but we do the partial trace over qubit 0. So again, if you're not familiar with this, just go over that series on density matrices and mixed states. Now, the next thing we need to be familiar with is what they call a qubit. And a qubit is basically similar to what we showed above. We have a unitary, but on the bottom qubit, what we are doing is we're taking the output and feeding it back to the input. Now, obviously, this is not physically possible to do because when we are dealing with quantum systems represented by quantum circuits, well, each line that represents a qubit is a physical item, right? So a qubit could be the spin of an electron or the energy state of some transmon. So what gates represent are actually time schedules of certain electromagnetic pulses that we're using to change the state of that physical qubit. So the concept of feeding back the output to the input would mean that we need to go back in time to take that output and reapply it at the input, right? So here, I don't know if this is just some conceptual idea of implementing this states called qubits, here represented by rho star, but this is what's given to us in the problem. And what we're told is that if we are able to do this, if we're able to feed back this state rho star back to the input, it actually converges to some value. So basically, as we can see here, this rho star is the same definition we had above for zeta 1, but here instead of row 1, well, we have just the same output here, rho star. And if we iterate over this over and over again, that means that we're going to end up with some specific value for rho star. So I see it somewhat like having a negative feedback loop in a control system where the system gets stabilized to a constant value. Now, since we would need to go back in time to reapply this output state to the input. A way that we can think about this in terms of implementing it in, I don't know, a simulator or in a physical system is just basically, reapplying the exact same gate with the exact same input row 0, and then taking the output of that gate and feeding it to an identical gate U over and over again. So basically that's kind of like applying this feedback loop, but by just doing it many times on an exact gate, then here at the output, we're just going to have this lower qubit value converge to this rho star. So this basically here is the concept of a timbit. So the timbit is this rho star state, which is basically a value to which we converge after iterating over and over again. And then we are also given the concept of what is called the timbit gate. So the timbit gate is basically exactly what we had above, but just focusing on the qubit that is not the timbit. So basically in this gate here we have two qubits, right? This rho 0, and then what it's going to end up being this state rho star. So if we just focus on this as an input and this as an output, and consider this feedback portion of it as part of the gate itself, well, we can define this timbit gate called TU, which is a map that takes rho 0 as an input, and then the output is, well, basically tracing out that timbit qubit, so tracing out over qubit 1 over this U dagger rho 0 rho star times U. Next, we're told, well, the reason we're describing this kind of new concept of timbits is because if we have this timbit gate available to us, it can be used to solve what are known as Boolean satisfiability problems, or SAT problems. And a SAT problem is basically a problem in which we have some Boolean formula and we need to determine if some Boolean variables make that formula to be true. So here's an example where we just have, f of x being given by x0 and x1, or x0 and the inverted version of x2, or the not of x2, right? And here we've done this example using a Boolean table, and we can see here that this formula f of x is satisfied or is equal to 1 for these 3 cases. So this will be a SAT problem. It will be, well, we need to determine for which values of x0, x1, and x2 f of x is equal to 1. Now what we're told is that using the timbit gates, we can solve an important part of satisfiability problems, which is determining if there is any element x that satisfies the formula. So the question is more of having a yes or no answer, and is, well, if I'm given a formula like this, are there any elements that satisfy it or not? So we don't need to find necessarily which elements x0, x1, x2 satisfy it, but if there's any of them that satisfy it. So an example where we will have a formula that never satisfies it will be this one, x0 or x1, and not x0 or not x1. So if we look at this truth table here, we see that there are no f of x for which this x0, x1 give us an output value of 1. So in this case, if we ask the question, well, is there any x that satisfies it? The answer will be no, there's no x that satisfies the problem. And this timbit gates can help us find that answer in an efficient way. So how is that done? Well, what we're told is that if we take the timbit gate and we use this unitary, which they call UNP, given by this expression here, then by implementing a quantum algorithm, we can efficiently find if there are any x's that satisfy this problem. Now, why is this the case? I'm not entirely sure. As I mentioned before, there are not any references given in this problem to try to figure out why is it that this gate works, and if this is just a conceptual idea and not something we can actually implement. Now, again, we are going to implement this 10-bit gate where the unitary that we're going to use is given by this equation. But now we need to frame this SAT problem in the form of a quantum oracle. So similar to what we do in, let's say, Grover's algorithm, right, where we're trying to find some marked element, we need to take whatever problem we have for Grover and code it up in a way that it can be represented as an oracle. So here we're going to do exactly the same. And what we're told is that the oracle that we're going to use is given by this UF, and this is very, very similar to the Grover oracle. Actually, I think it's identical to the Grover oracle in a modular form. So basically what this expression is saying is that our U of f is going to be the sum of all x elements for n qubits, where if this f of x is equal to 1, we're going to apply an x gate to an n plus 1 qubit. So the first n qubits are here in this outer product, and then we have an additional qubit where we are applying an x gate. So if, for example, there is no f of x equal to 1, so if all f of x's are equal to 0, then this x gate never gets applied. And what the sum is just basically an identity matrix, right? So, you know, this elements represent just all 0 matrices where only we have a 1 in the diagonal number where we have x. So for example, for this outer product of 0, 1, 0, that will be 2, right? So we have a 0 and 0, a 0 and 1, and then a 1 in number 2, and then zeros everywhere else. So if we add up all of the elements in that basis, well, we're just going to end up with an identity matrix. So that will give us just a U of f that is an identity for all those outer products, plus the identity of that last qubit where we never applied that x gate. So we get an identity of n plus 1 qubits. Now, if there is an x gate applied, well, that's just equivalent to having this type of circuit, right? So if we have, for example, f of x equal to 1 for element 0, 1, 0, that means we just need to apply an x gate on this n plus 1 qubit, right? The first qubits are the first n, and that's just a multi-control CX gate where the controls are just given by the string that we're interested in. And if we have more than one element, then we just apply more of these. So for example, if we had another element, let's say 1, 1, 1, that also satisfies this equation equal to 1, then we would also add an additional multi-control CX gate where now all our qubits are equal to 1, or the qubits that activate that CX gate are equal to 1. So that's just basically what that U of f is. So basically apply a control x gate on an additional qubit n plus 1 whenever our x satisfies the f of x equation. And then lastly, well, we just need to implement the algorithm. So what they tell us is that the algorithm works in the following way. We start with our first n qubits that represent the state x. So x are all these possible elements that are going to be part of our f of x. We place them in a superposition by just applying Hadamard gates. Then we apply our oracle U of f, which we just described above, with an additional qubit. That's the n plus 1 qubit, right? On which, after applying the oracle, we apply our 10-bit gates a number of q times. So this is the part that makes this interesting, and where we're told that if we apply this 10-bit gate using this UNP unitary, then that's going to allow us to determine efficiently if in this U of f there is an f of x that for any element satisfies this f of x equal to 1. Now, how does it work? Again, we're just told that this density matrix of the last qubit is going to be equal to 1/2 times the identity times this function g of q and s times the poly z matrix. Now, this q here is the number of repetitions that we apply of that 10-bit gate, and this s is the number of solutions that give us this f of x equal to 1. So if, for example, we have x equal 0, 1, 0, giving us an f of x equal to 1, and I don't know, x equal 1, 1, 1, also giving us f of x equal to 1, that will mean that s is equal to 2. And then the last part is that we're told that if s is equal to 0, then this function g is equal to 1. So we end up with the density matrix 1/2 of the identity plus the poly z gate. This actually is equal to the matrix 1, 0, 0, 1, 1, 0, 0, 0. But if s is different than 0, so if we have at least one element that satisfies the equation f of x equal to 1, then as we increase the number of iterations q, the number of applications of this 10-bit gate, then the output density matrix tends to just 1/2 of the identity. So if we apply these 10-bit gates enough times, we can see or check if we get a density matrix equal to this one, right? And if we do, that means that we have no marked elements. But if we get the identity matrix, then that tells us that we have at least one marked element, or one element that satisfies the equation f of x equal to 1. So I know this is a lot to take in. It's a lot of information. This is why I think this was the hardest problem. And these are all very new, different concepts that at least I was never exposed to. And it took me almost a full day to solve the challenge. But I hope this was clear enough. If not, then just add a comment in the section below and let me know if there's anything that needs more clarification. Now, with this, let's go ahead and go into Penny Lane and code up the solution. So we're gonna do several imports here. So we're gonna import Penny Lane, NumPy. I'm also gonna import SymPy and SciPy. SciPy we need because there are some helper functions that are used within the code that is given to us. And SymPy, I'm importing it so we can display some matrices of what we want to do. Here, the first thing we're going to do is define the UNP matrix. So just a reminder, the UNP matrix is the unitary of our 10-bit gate that we are told that it's kind of a magical gate, that if we use that one in a 10-bit gate, it allows us to efficiently find if we have a solution to the satisfiability problem or not. So let's go ahead and just display that here. And we can see here that this matrix is, it maps the state 0, 0 to state 0, 0, the state 0, 1 to state 1, 0, the state 1, 0 to state 1, 1, and state 1, 1 to state 0, 1. Next, we're going to define the function that calculates our 10-bit. And that's going to take as an input the unitary U of the 10-bit gate. So that's going to be this UNP. It takes also row 0. So row 0 is the input density matrix of qubit 0. Then row is the initial state of the 10-bit. So this will, after some number of iterations, which here we input as n iters, this is going to converge to that row star. So then we're going to create our device and we're going to use the default mixed state for this one. And then we're going to have 2 qubits, right? Then we're going to define our map CU, which again takes the same inputs. So U, row 0 and row. And then First, we need to initialize our input state row 0. Then we initialize our input state row. And then we apply the unitary U. So basically here, that will be equivalent to just implementing what we had here at the beginning. So we initialize row 0. Here it was labeled row 1, but this bottom one is what we are calling in this function row, and then apply this unitary U. And then this is going to return the density matrix for that bottom qubit. So if we see here, what we're implementing is we're initializing this state row 0 and initializing the state row, then applying this unitary U, and then that circuit is returning the density matrix here at the output of that qubit 1. So this circuit we would just implement it in code is basically this block with the bottom qubit as the output. Now we're going to define this row star equal to the first application of this gate. And then we're just gonna iterate for a number of iterations that is gonna be given to us to find the final row star. So this is the initial value of row star after one application, but then we're going to do range from 1 to n iterations. And then we're just going to apply this CU gate, but now we're going to always use this row star as the input to that second qubit, right? So basically what that is doing is just reapplying this gate n times, right? And then this overall function is just going to return the final value of that row star. So here we can just take some initial value of row and row 0 that is given to us, and we could go ahead and display the input value of row. So that's some value that is some matrix that is given to us, and then we can calculate the final value of that row star and show that. And basically what we see here is that row star converges to this final matrix. Next, we're going to define a function that we're going to call apply timbit gate. So with the function above, we calculate the timbit, but now we need to define the timbit gate, which, if you remember, takes as an input is the top qubit of this U gate, and gives us the output also the top qubit after we apply this map TU, which is taking the partial trace of the output state once we have found that converged value of row star. So to this, we're going to pass the same unitary UNP, row 0, and now timbit. And then this is going to look very, very similar to what we did above. We're going to define a device, a Q node, and then we're going to call this Q node TU, which takes the same inputs, U, row 0, but now instead of an initial row, it takes as an input a timbit. And it's basically the exact same circuit we had before for this CU gate. But then at the output, what we're doing is we're calculating the partial trace for qubit 0 instead of qubit 1, right? So that gives us the output on the top qubit, which is what we need for this gate. And then this overall function just needs to return the evaluation of this gate. And as before, we can just see what we have for the input row 0 and what we will get at the output after applying that gate just one time, right? So this is our input state for that gate, and this will be the output state for that gate, that timbit gate. All right, and now we're going to define a function that is going to implement our algorithm. So we're going to call it SAT. It's going to take as an input UF, which is our oracle, right? So that's the one that's going to have our marked elements. Well, we don't know yet, right? It's going to have either a marked element or more, or no marked elements. Q, which is the number of applications of the timbit gate on that last qubit. rho, which is the initial value of our timbit, right? So as we said before, it doesn't matter what value we apply here, the timbit would eventually converge to a rho star, which is our timbit, and then the number of qubits. So here first we need to define a Q node for the first part of our oracle, so the part that is going to apply the Hadamard gates to the first n qubits, and then the oracle itself. Now here, this was also a very confusing part in the problem. This n bits here is not the number n that we've been discussing before. This is actually n plus 1. So this is the number of qubits of our element x plus the additional qubit for the timbit. So we define our device and a Q node that here I'm going to call just HUF. So H for the Hadamards and UF for the oracle. And it's going to take as an input the matrix UF, rho, and n bits. And here I'm going to apply the Hadamard gates using this broadcast function. And as you can see, I'm applying it on n bits minus 1. So those are our qubits that correspond to the element x. Then I'm going to use this qubit unitary to apply our matrix UF, which is our oracle. And that's going to go in all qubits. And then we're just going to return here the density matrix of the last qubit. So here I'm putting it on n bits minus 1, which that's the one where we now need to apply our timbit gate. So now I'm going to define this rho 0 as the output of this gate here, which includes a Hadamard and the oracle, and it gives us the density matrix of just the last qubit. And then we just need to apply our timbit gate a number of q times. So we're going to use a for loop for that. And then what we do is we create the timbit associated with the gate being applied on a given point, and then compute the new output after each timbit application. And then what we're asked to return in this function is actually the probabilities on that output rho after applying it q times. So I'm going to define a Q node for that is going to take as an input the last density matrix from after applying the timbit gate q times, and then returns the probabilities on that qubit. And then by calling this function, that gives us the output probability values. So if now we go ahead and define our oracle, that's our UF, which is given to us. And then we're going to define that initial rho that will converge to rho star. And then we're given to solve this just for one iteration. And then because of the way the oracle is defined, we have a total of 4 qubits. And then all we need to do is just call that function. So let's go ahead and print the output of our SAT function. And here we have the output probabilities for applying the timbit gate only one time for this particular oracle. So if we go here to this given inputs, so for one application, we get this probability distribution, and that's exactly what we got. And then the next one is applying it twice. Then we get this probability distribution, which matches what it's given here. Now, an interesting thing to do here is to actually check that what we were told is true, right? We're told that if we apply this timbit gate here, so number of times q, well, if we have no mark elements, right? So this S is equal to 0, this output matrix should be equal to this matrix 1, 0, 0, 0, right? And if we have at least one mark element, if we apply this gates enough times, then it should converge to the identity matrix. So let's go ahead and actually check that that is true. So first here with the oracle that is given to us, we do have one marked element. So Let's go ahead and do this for, let's say, 5 iterations. And instead of returning the probabilities here, let's return actually the density matrix. So let's comment this out and let's actually return the density matrix at the output. So basically all I did is just replace this probabilities by density matrix. And here, instead of printing, let's just do this matrix that will render in LaTeX. So if we apply this 5 times for some mark element, here we see that this density matrix starts approaching 1/2 of the identity matrix, which is what we're told if we apply this gates number of q times where q is large enough. And here we just did it for 5 applications. So let's now put no mark elements, so all identities. And here we see that is very close to that 1 0 0 0 matrix. And maybe let's do it for another oracle where we have more than one mark element. So let's put several, x here, which is going to put more than one solution that satisfies f of x equal to 1. And here we see that it is still giving us an identity matrix. So it's telling us that there is some mark element there. So I know this was a lot to take in. I hope that it was clear enough, but if not, just post in the comments below. Let me know if you have questions, and I hope to see you in the next video.